Welcome to another video explaining the universe using the particle model. Well, today's video is the second video on the gyroscope, and it asks the question, can a gyroscope move up? The previous one was basically on anti-gravity, trying to explain why the gyroscope stays in its position. And the key question in most types of motion is, what's its next position? And we find that the high speed dominates, and the force of gravity is weak and has some effect, but the high speed keeps the gyroscope rotor in place. Today we're talking about, is there a way to make the gyroscope move up? We often see it move down, fall down, but not move up. For example, can this gyroscope move up? Never seen it do that. We've seen it stand up completely upright. Then when it, for some reason, tilts over, it starts precessing, slowly moving down until then it falls down. It moves slowly and then it falls. But we don't ever see it really move up. Well, I'm going to use this video. It's a very interesting video. I recommend you see the whole thing. And I'm going to explain the setup of this experiment the gentleman is doing. And basically, he's controlling this gyro, this rotor, keeping it at high speed at all times. The setup is such that the axle is horizontal and the gyro, the rotor itself, is vertical. Now, what he has here is actually stated in the video that these two bars, the sections, are equal, or nearly so, and he claims this is balanced, and yet he has a wire hanging here. And okay, so, but it does hang nominally vertical from looking at it. It has a battery and a controller here, and two wires going to the rotor. Has a DC motor connected, a DC motor that is controlled remotely by this, and you can't see it, but this one you can see. There's a lever here for controlling this latch over here, but this lever is standing straight up. It's nominally at 50% speed, and he can slow it down by pushing the lever back, and he can speed it up by increasing the DC and control the speed. But during the whole experiment that he's doing, the demonstration, the speed is constant. This is the setup, and it's just sitting there, and it does in the video, while it doesn't sit still, it does precess in there. And next time when I talk about precession, I'm going to mention something about that. Okay, now the question is, what he does, one of the first things is he literally forces it up. He pushes it up with his hand. The question is, will it move down? Well, yeah, of course, that's what we expect it to do. The high speed keeps it in place, and the gyro, when he pushes it up, is above the pivot point, and that's critical in this. This is a pivot point that allows it to move up and down and around. And by the way, there's this rod that's vertical can move around as well. So he pushes it up, and then you watch it precess, and you watch it go down. This is what you see in the video. Okay, so the gyro does move down. Gravity pushes the rotor down. It doesn't fall down up when it's above the pivot point. It doesn't fall down. It moves down slowly. Again, the high speed dominates and keeps the gyro basically in the gyro wants to stay here. It doesn't want to move up. It doesn't want to move down on its own. but we have the force of gravity, what we call in the particle model G1 gravity, and F1 is the net force of gravity. This is caused by the Earth. I mean, this demonstration is being done, and so this is the gravitational force of the Earth on this part of the gyro and this part. Of course, it happens all the way across the rotor. However, this one is weaker than this one because vertically this is higher, it's weaker, but by a very small amount. Gravity, is Newtonian gravity or G1 gravity is very weak, and now we're talking about the difference between these two. You can break this force vector into two components, one in line with the rotor and one perpendicular, one in line with the rotor, one in particular. But yet again, there's a net force this way pushing, and there's a net force this way pushing, this one being stronger than that. And when you push this with a net force down here, it's going to cause this to move down. And it's going to move down slowly because the force differential is very small. Then it stops. In the demo, it comes down to the setup position. The high speed continues to hold the gyro in position, but when this is truly vertical, when the rotor is in line with the force of gravity, there is no horizontal component to push it down further. It won't go down further. In order to push it down further, you'd have to have a higher force up here and a lower force here, which is not going to happen. Gravity is smaller here and weaker here. So it's in line, it stops. As it drops slowly, it precesses and drops to the horizontal position because there is no horizontal force of gravity. So it returns to the same setup position. That's all I'm showing there. The picture that was at the end of that. Well, now the question is, will it move up? Well, in this case, the gyro is pushed down below the pivot point. It's still running at the same high speed. So what happens? The gyro moves up. The high speed, again, it's the same thing, continues to hold this in position, even though it's down below the pivot point. Doesn't change that issue. G1 gravity has a very small force differential. This is weaker, this is stronger. The vector component of this pushing here is stronger than the vector component here, so there's a net force on the bottom half of the rotor, and because it's below the pivot point, it's going to move up. Forces of gravity. It's going to move up slowly. So it does move up, but keep in mind, this is a special case where you have a pivot point and you have another arm. This arm is extended up as well. I just didn't draw it. And so we move on, and then it stops. It moves up, it stops. It's the same thing all over again. It won't go up anymore. It won't go because there is no force differential. You have to force it up, and when you force it up, it moves down. When you force it down, it moves up. So yeah, a gyro can move up, but in this special case. What about an experiment? How about we do an experiment, use this setup, and what we're going to do is increase the speed of the gyro. Now, he stated in this that he's running it at 50% speed, so let's put it there. And then we let it settle to its setup point, which is horizontal, and then slowly increase the speed. Will it move up? Well, I just stated in the previous slide, if I can go back here, gravity isn't going to move it up. So what we're doing is we're going to increase the speed and see if it moves up. Well, why would I even say that? Well, I haven't covered, I covered this torque equation in the previous video. Torque is the force, and the force is a time rate of change of momentum, and momentum is proportional to the speed. So as you increase the speed during the time you're increasing it, therefore it's accelerating. This is going to have a value, and it's going to create a torque according to the equation in the upward direction. If that torque is greater than the force of gravity, it should move up. The equation implies, to me, it implies it ought to move up. I would say no, it wouldn't. I would love to have the guy do the experiment and show that when he increases that speed, that it stays in the horizontal position. So in summary, when the rotor is in line with gravity, there is no force pushing it up or down. Also, when the rotor is perpendicular to gravity, that's when it's in a horizontal position, it's perpendicular to gravity, there is no force pushing it up or down. It stays there a long time until something kicks it out. And it tends to stay in these two positions because of the high speed. When the rotor is below or above the pivot point, in this particular case of this experiment, there is a small gravitational force difference that will cause it to slowly move, either up. If it's down, it'll move up. If it's up, it'll move down. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.